Hello and howdy, ladies and gentlemen. Root Beer here, and I'm going to be wrapping up the 2011 Euclid paper with question number 10 right here, which seems to have something to do with this triangle over here. But let's see here. And hopefully you've given this one a try. If not, I'd recommend you pause it and at least try and do something like A or B. You might not be able to do all of it, but see how far you can get into question number 10. Okay. What have we got? In the diagram, twice angle BAC is the same as 3 times angle ABC. So this angle over here. Okay. K lies on BC, so that KAC is twice KAB. Okay, so we're being told some things about angles, and then it looks like we're just giving names to sides. So A over here, BK is X, AK is, they're calling it D. Opposite the C, you get the little c, and then it looks like we have a B here. So I guess we could call this A minus X off the top of, just right off the bat. So this is our setup. Some angles are, like, the only thing that's really prescribed, the only thing that tells us anything about this triangle are these angles. And sort of the ratios or the, yeah, I guess ratios between them. Everything else is just they're saying, hey, this is a named length. They're not telling us B is 5 or something like that. Okay. We got A, B, and C. A, prove that D is equal to BC over A. BC over A. Now, to me, with all these angles here, that strikes me as something I might do with similar triangles. We also want X is equal to A squared minus B squared over A. Now that makes me think cosine law, maybe. Maybe there's a way to do it with similar triangles, but with the squares in there, I definitely feel like we might be looking at although it's a difference of squares. If I write that as A plus B times A minus B over A, that's looking, it's a product of two things on top over an A, and that's what we have to show with the first one, and I thought that might be similar triangles. Well, let's see what we can see. Now they give us names for the length. They don't give us any names for any of the angles. So what was it? This one was the smallest one. Let's give him a name like Theta. Actually, I should probably letter these things before I get lost. This was K, I think this was B, and this was A. Yeah, for some reason they went counterclockwise. Oh, that's fine. But this one here was KAB was definitely the small one. You double it to get KAC. So we'll get 2 theta over here, which means overall we've got a 3 theta here. And so BAC, so that's 2 times 3 theta is 3 times the other angle. We might want to write some of this down, but I think I'm verbally explaining it. I suppose you could say 2 times angle BAC is 3 times angle ABC. So 6 theta is 3 times angle ABC. So 2 theta is angle ABC. So we get another 2 theta down here. So we have a 2 theta here, we have a 2 theta here, little theta here, and then a big 3 theta here. Okay, so some angles there. Now the similar triangles, I've got 2 thetas. Oh, okay, so we could say something like, if you've got 2 interior angles, you extend one side, this exterior angle, so you can say bi-exterior angle theorem. Angle AKC is angle KAB plus angle KBA. And so that should be 3 theta, and then, I got a little similar triangle here. And what was it? C is over here, A is the big one here, we got X down here, a minus x here, b here, and d here. So we can see, all right, so they got the c in common, so we'll write that one first. Triangle C is similar to triangle C, so CAK, and K is the one with the 3 theta, which is A on the big triangle. B is the one that has the 2 theta, which A does in this smaller triangle. Okay. So because they're similar, what can we say here? So CB, now the ratio CB over CA, this is why it's important to write them in the proper order, because now I can say CB is to CA, and AK is D, so that is the same as BA is to AK. We'll say which we can write. So CB, there's no A in there, so that's got to be A. CA has got to be B. BA is the C, and AK is D. So I have D on the wrong side, or well, on the bottom, but we can multiply through AD is BC, and then we can bring the A down below. Okay, so I have this nice relationship. This product here is kind of cool as well. I don't think it's actually going to mean anything, but it's nice to have things that are not just as a single fraction. I'm not the biggest fan of fractions, but okay, so we did that. Now, we need to show x is a squared minus b squared over a. I wonder if so we got A, or we got X, we got C. Is there a way to make another triangle involving X and maybe do something like extend A by B down there, but I wouldn't have X where exactly I want it. Maybe we could extend this B over here by A and then come across or something like that. Not entirely convinced that'll work either. So I might have to talk about cosine law or something here. They want a squared minus b squared over a. Now I did write it as a plus b over a minus b. Could we drop something like k over here? And would that necessarily then have to be like a minus b up here, and this is a plus b? I mean, it was wishful thinking, but I'm just trying to think, can I get another similar triangle involving this x here? Or maybe we should use the relationship between a and a minus x. Let's think for a moment. CK is x. So CK is to CA as let's get ones involving A and B. So that's so the same as CA is to CB, which is so CK is A minus X, CA is B, CA is still B, and CB is A here. Oh, that's going to do it. So then we again multiply by A and B. No triangle extensions or anything like that to get an A plus B or an A minus B. So A squared minus ax is the same as b squared. So there we get another nice expression with no fractions in it. And then we can bring the b squared over here and the ax over here, just changing the signs, and divide by a, and we're all set. So we wanted that one, and we wanted that one. There we go. Some nice little similar triangles there. All we had to do was sort of hunt through these angles here, because and that's the big thing to realize at the start. They're really only telling you a bit about angles. They're not telling you a thing about these ABCs. They're just giving names to them. That's it. Okay, B part. Prove a squared minus b squared times a squared minus b squared is equal to a, or plus ac is the same as b squared c squared. Okay. Well, I have an expression here for a squared plus a squared minus b squared. I can replace it with ax. So notice I see a squared minus b squared, and then we do a squared minus b squared again, and then I think it's plus ac. It's plus ac, right? Yeah, plus ac. So I can immediately say, and we might want to, if you're going to refer back to things, you might number this as like 2. You could have a similar one. This could be 1, or they don't even have to be that. I mean, you could say 1 here and 2 here, and then as your first step in part B, rearrange this 2 to that one. That's fine. But we can see that's ax times ax plus ac. Now I want to pull out some a squareds from here. So I've got x times x plus c, and we've got a squareds. And what do we want this to be equal to? We want this to be equal to b squared c squared. And if I divide through by a squared, I'll get x times x plus c is b squared c squared over a squared, but we just showed that that's the same as d. Well, d squared. Right? So just take out the squares from everything, and you'll get d by part to a, by my equation 1. So what I need to do is show that x times x plus c is the same as d squared. Which is sort of another one of these no fraction statements, but I suppose we could try and do something like show x times x plus c over d is the same as d. That could be something. So might be more similar triangles, I guess. Now we do have an x in, so c's down here, x is here, d is here. So cx and d are really closely related in a triangle, but I don't see any x plus c's. Now, one thing we could do is extend this by x, and then, I don't know, maybe extend this to a bigger triangle, or something like that. C, A is over here, B is over here. What I'd like, if I'm going to do that, I want another similar triangle. So I don't think I just want to duplicate this or sort of extend things out and just have this would then be Rx and this whole thing would be Rd, and then we get Cx. There might be a way to do something with that, but I put up this R and some other stuff. Or would we? Yeah, we might. So, is there a better way to do this? Is there another? And maybe I'm not supposed to be extending this x here. I mean, it certainly didn't help me when I did it as a thought experiment back here. You know, I thought maybe I could extend down here. Maybe I'm looking at the wrong thing. What do we know? We know that this is 2 theta here, and this is theta. This was 3 theta, this is 2 theta as well. Now, if I'm going to extend this, I want another triangle. What sort of another triangle? Like, do I want to keep this A here, or this theta here? Or do I want to? I guess we couldn't put theta up here or anything. So I'm gonna make I'm trying to make a new triangle here. That's my thought. Now this angle, I have no idea what it is. I mean, it's 180 minus 3 theta, but I don't have a whole lot of information on what theta is. I don't think we have a fixed theta necessarily. Maybe we need to go hunting for that. But I have the option of either extending the triangle this way and keeping the theta here and the dot here and the 2 theta here. Or we could do sort of how this triangle and this triangle are the same, but as you extend it, you sort of switch it around. And so what would we get? We get some sort of sort of extend it out like this. And then this becomes 2 theta, and this becomes the dot. And that doesn't look very good, but I might just have a very poorly drawn picture. So would something like that work? Now this is, with this little x here, this is isosceles, so we'd have a dot here. And if this is going to be 2 theta, then that means these dots are each theta. Oh, and that means I can figure out what theta is. Theta's got to be 45 degrees. That's kind of cool. Assuming that yeah, no, that should work. Extend it by x, you'll get the isosceles triangle. So that and that are the same. But that doesn't necessarily mean that you've got 2x here. Or 2 theta here. That's the hope, is that extending the triangles that way gives you 2 theta. I have to be careful that I don't just imagine that I've got what I want. So if I extend the x's and do that, I get these two angles are the same. Ah, but then they must add up to 2 theta. There we go. So then the dot must be theta. So this is theta, this is theta. We got our c plus x along the bottom. We've got an x here. We've got a d here. What's this length here? So here's what I'm going to do. I'm going to start actually writing this up. So let's say extend, we'll call this point D. Extend AB to D so that BD is equal to X. Then triangle KBD is isosceles. And you can always refer back to your pictures. You can say as shown. So I'll say by exterior angle theorem again. Angle KBA is angle KDB plus angle DKB, which is 2 times angle KDB. But of course that's 2 theta. So KDB is theta. And so we've got both of our thetas shown. So we'll redraw the picture again a little bit bigger. Theta here, theta here, theta here, 2 theta here. And where did I want to go from there? So this is x, this is x. This is D. Oh, we get a bigger isosceles triangle here. Call this K, we call this little d This was B, A, C. So then what I can say triangle KAD is isosceles. So KD is also equal to D, so I've got that going for me. That's kind of nice. But in order to do... Is that enough to do the similarity, or do I definitely need this bit here? So I'll say looking at angles, we have triangle KAD is similar to the apex here is B, so BDK. Then AD, that's my x plus c bit. That's the whole reason we extended this, is to KD. Well, let's say DK. Yeah, DK, just to keep the order right. So that is to DK as... we need another D in here because we need a D squared. So we'll say is to KA over BD. Or x plus c over d is d over x. So x times x plus c is d squared. So now I can take that, and so from this, multiplying both sides by a squared, we see ax plus ac is a squared d squared. But I did have that nice little non-fractiony fact over here, or you can just reference what I've called 1. And we can say, all right, this a squared d squared, this is ad squared. Well, that just turns into bc squared, which is b squared c squared, which is what we want. And over here, this expression is the ax is a squared minus b squared, and that ax is a squared minus b squared. So we get my a plus ac there, and there we go, as desired. Now, I just want to go back here for a second. I could have sworn there was a way to show that this angle here was also theta, and therefore theta needs to be 45. I want to explore that again for a moment. So originally what I was trying to do was is to make this triangle, this red triangle here, similar to this purple triangle. Perhaps not the best choice of colors. Is that still true? Because if it is, then I know that this has got to be 2 theta, so then this angle over here is theta, this is 3 theta, and that forms a full line. So I'd have x squared, or c plus x, this side, is to the old long side, that is to say d, as my new short side, d, is to my old short side, x. So yes, this does still hold, so I can show that this is theta and that theta must be 45. So I don't know if we'll need this for C part, but I definitely want to write it out. So we can see also that is there a nicer way to do this? Say that this, just by looking at the angles, is there a nice way to do it? Because I'd like to be able to prove it just from angles. Hey, if that's the case, then wouldn't C and X be the same thing? Yeah, they'd have to be. Now, do I believe that that's true? Because if not, I mean, I'm happy with the angles over here, but maybe I've screwed something else up. Well, okay, if I want to show that KAD is similar to the A is the one that I want to keep as the apex. So we'll say AKD is similar to AKB is that one, and then D is the other new point, but they swap around, so ADK. So I need to show that AK is to AD as AB is to AK is to KB, or is the same as KB is to DK. So can I show that? So AK is D, AD was X plus C, this was X, so yes, that one holds. KB was X, and DK was D, so that one holds, and so does this one hold. So I'll say since these ratios hold. If the ratios of the side are all the same value, which in this case is X plus D, then they must be similar. So then what I can confidently say is the angle AK to D must be the 2 theta. Just want to go back, make sure I got it right. AKD is 2 theta. And we conclude something. That AKB must just be theta. I can see that 4 theta is AKB plus the 3 theta for AKC, which is 180 degrees, so theta must be 45 degrees. And now I'm worried. I'll tell you why I'm worried, because we've got theta is 45 degrees. I've got 2 thetas down here, so that's a 90-degree angle, but I've got 3 thetas over here. So we've got some very, very bad stuff going on here. Because this would be 135 degrees. And then this would have to be negative 45 degrees. Well, I'm not comfortable with that. So where, oh where, is my error? Two times 3 theta, 3 times 2 theta. This whole thing was a 3 theta. This has got to be a theta. That's got to be a theta. This has to be a full 2 thetas. Wait, maybe these, I mean, when I extend it, they don't look right. So am I just wrong with this similarity here? Am I missing something? I'm talking about AKD is to ADK. Oh, wait, no, AB is C. So unless if C and X are the same, but I can't guarantee that. Okay. Alright, that was driving me nuts there for a moment. I was getting impossible triangles. So I can ignore all of this. Okay, fine. So I'm a lunatic. That's fine. You already knew that if you're a long-time viewer. Okay, we'll just pretend that I did this part here, B part, and that I didn't try to find any angles, because it turns out I can't. At least not yet. Okay, C part. Determine a triangle with positive integer side lengths A, B, and C, and positive area. Okay, wouldn't it have... I guess maybe zero area if we had a degenerate triangle. I don't think they really consider those to be triangles. Positive area that satisfies the conditions in part B. Okay, well, we know if you make a triangle with these angles, then you'll be fine. Can we show that this condition is necessarily tied to these angles? I suppose if you showed that, yeah, it's completely quadratic. So any factor r would, for similarity, would come out. So yeah, this shouldn't matter. The specific a and b, you can always scale it quite nicely. But maybe we should write that down. Well, we'll write it down if we need it. But showing that that condition holds. Okay. Well, let's just play around with this. Now, we do know we could change this in terms of like x's, and we could add some d's and stuff. Now, the reason I don't want to do that is because they're just asking me for a, b, and c. And so they've already given me the expression in a, b, and c. Why go ahead and add in d's and x's? Maybe we'll need to, but I feel like leaving it like this would be fine. Now, what, if anything, do we want to do here? I suppose we could expand a whole bunch of stuff out. So a to the 4 minus a squared b squared plus a cubed c minus a squared b squared minus b to the 4 minus a b squared c is equal to b squared c squared. So we got that. I don't like working with these not quadratics, quartics for A and B. But C doesn't have that problem. C is just quadratic. So I wonder if we bring everything over to the other side. I'm going to say, okay, plus ab squared minus a cubed c. So those two have been brought over to the other side. Their signs switch. And then we get this other thing, which is like a constant term. So b to the 4 minus, which actually turns into a plus, 2a squared b squared minus a to the 4. That's really close to being a squared plus b squared all squared. So I might want to do something about that. But now here, this is this has no c's, so it's constant in terms of c. This is constant, has nothing in terms of c, and then nothing in terms of c here. But it looks like we've got a quadratic in terms of c. So I should be able to find c in terms of a, b. And I'm going for c again because the a's and the b's are all to the power of 4s, but the c's at most are a power of 2. Okay. Now, do I want to do something about turning this into a plus a to the 4? Or should I say it's a squared minus b squared times a squared minus b squared, and then you get the thing in terms of c and then the thing in terms of b? That might be cleaner. Oh, wait, no, I'm a nut. The minus minus, this should be a plus. So it already is a constant term. So I'm just going to rewrite this b squared, a squared. I'll say a b squared minus a squared. It might turn out that we turn b squared minus a squared into its own variable e or something. But we'll say minus b squared minus a squared squared. That might be a little nicer to work with in a moment. Let's not forget our c here. Okay, so we can say something like by quadratic formula, c has got to be negative b. So we'll say a squared minus b squared. I'll just introduce the minus sign by flipping those two around. Plus or minus, squaring that, so that'll be a squared and a squared minus b squared squared. I suppose it should be b squared minus a squared, but squaring it then doesn't change the order. Minus 4a c, and c was minus b squared minus a squared squared, so I'll change this to a plus, and it's being squared, so also you can just sort of swap the order there. Okay, all over 2a, which in this case is 2b squared. Okay, there we go, get that. Plus or minus. Now, I notice I've got a factor of a squared minus b squared squared and a squared minus b squared squared. So I could group them together. I could also bring them outside the square root sign at the cost of a square. But then the order does matter. If b is bigger than a or a is bigger than b, we're going to have a bit of a problem. I'm going to, just because when I bring it out, I want to group it with this a squared minus b squared. So I'm going to make the assumption, and you would need to write this down. Assume a is greater than b. Now this might backfire on me. There might be something more in the math that tells me b should be. Actually, let's go back and look at the sides for a moment. Have them labeled. A is over here across from a 3 theta. B is over here across from a 2 theta. So actually, no, A should be bigger than B by virtue of being across from a bigger angle. So I don't have to make this assumption. But I should point out A greater than B, since 3 theta is greater than 2 theta. So the square root of a squared minus b squared squared is a squared minus b squared, not flipping the sign around. Because remember, square rooting something that's been squared doesn't just automatically cancel out the square sign. It sort of introduces an absolute value, so you do have to know that the thing you were originally squaring was positive, which now I have confirmed for myself. Left under the square root sign, I guess, is a squared plus 4b squared. Okay, and then divide by 2b squared. Now we want a, b, and c to be integers. So I guess this top bit has to be a multiple of 2b squared. But we also definitely need the square root of a squared plus 4b squared to be an integer as well. So let's focus on that. Let's see if we can get an expression for that first. So we need a squared plus 4b squared to be itself a square. So for some integer k. Now, 4 is a square, so this is really a squared plus 2b squared. A squared. So I've got a square plus an integer square plus an integer square is another integer square. A, 2b, and k are a Pythagorean triple. So that's kind of interesting. There's a Pythagorean triple being hidden in here because I know a and b have to be integers, so a and 2b are integers, and we need this k to be an integer. So I doubt it's as simple as just picking a Pythagorean triple, but we could try something simple like 3, 4, 5. So this is just me exploring it. Try 3, 4, 5. So A is 3. B would be 4 over 2, which is 2, because 2B would be 4. 2B would be 4. And then K is 5. So then we get C is A. And you'll notice here the A is bigger than the B, so that's actually something we would need to watch out for. You'll get 9 minus 4. Plus or minus, we don't need that square root anymore. We'll get 9 minus 4 as well, times k, which would be 5, all over 2b squared, so 2 times 4. So that's 3 times 5 plus or minus 25, so 15 plus or minus 25 all over 8. We'll have to go with the plus, so c is 40 over 8. 5. So we got an integer there. So A is 3, B is 2, C is 5. Does that work? Well, they're definitely all integers, but you're not going to have positive area here because if I've got 5, unfortunately, you can't put a 2 and a 3 here. The only way the 2 and the 3 could meet is if they lie flat against, and we get what's called a degenerate triangle. So the problem here is we've got this sort of extra condition. We need to satisfy the triangle inequalities. Well, I'll say triangle inequality, but because I'm not sure which one's going to necessarily end up... Like, C was the biggest one here, but is that always going to be true? So the biggest thing needs to be less than the sum of the other two. And I'll just write all the ones out because I don't know which ones I'm going to need. Basically, biggest one needs to be less than the sum of the other two, and we don't have that here. But it is kind of nice that I didn't have to worry about this 2b squared down here. Okay. So do I start worrying about the 2b squared, or can we try another Pythagorean triple? Like, are they all going to be sort of degenerate until I hit upon the right thing? So what if I tried 5, 12, and 13? And by the way, I can just sort of guess and check my way to success, because all they're saying is determine a triangle. We've done a lot of the theory to explain why these are good guesses. We're not just plucking numbers out of thin air. Here, A would be 5, K would be 13, B would have to be 6. So that's a no, because we need B to be greater than A. Or B, we need to be B to be less than A. 7, 24, 25, that's going to cause the same problem. Our odd thing is way too less than my even thing. So let's think of another Pythagorean triple. Well, I suppose we could do 6, 8, 10, just a scaled up version of the 3, 4, 5 triangle. But we could make 8. B could be 3. And then K could be 10. That might work. So we'll have 8, 64 minus 9, plus or minus 64 minus 9, and then times 10, all over 2 times 9. Then we'll have Oh, 64 minus 9 will be 55. So I have 8 times 55, so that's 440 plus or minus 550. So definitely the plus category there. Divided by 2 times 9. Now this looks promising. So we'll have 990 over 18. Divide by, so you'll get C is 55. But that's way too big. So it looks like if I scale up 3, 4, 5 triangles, I still can get a solution. I don't have to worry about this 2b squared here, but the C is growing much, much bigger than the A and the B. All right, let's try and think of other Pythagorean triples. So here's one that doesn't come up a whole lot, but 8, 15, 17. My A would have to be 15, my B would have to be 4, K would end up being 17. Now C would be 15 times 225 minus 16. Should be 209. Plus or minus 225 minus 16 times K. So, I mean, one thing I could do is I could definitely say, let's just take out a factor of A squared minus B squared. Then it's always going to be A minus K, or A plus or minus K. And you're always going to have to do the plus because K has to be bigger than A because K is the hypotenuse. Okay. So there we go. Okay. So it definitely have to be the plus. Get rid of that. All over 2 times 16. So that's b squared. So let's see. We'll have 209 times 32 all over 32. So C is 209, and that's not good for me either. So the C's are too big. Now the C wasn't that big when we did the first one. As the A's and the B's are getting really separate, and so the A squared minus B squared is being a bit of a pain. So I'd like A and B to be close in value if I can. So maybe try something like 20, 21, and 29. So my A is 21, my B is going to then be 10. Well, then the A and B aren't close again. This A and this B were kind of close. They were the wrong way around. And the A and B were close when I did the first Pythagorean triple, 3, 4, 5. That wasn't bad. Here the A and the B are too far apart, and so we get this 209, this ridiculous, absurdly huge number. Doesn't help. So I need to pick one where the even number in my triple is just a little more than twice the odd number, the A. And I'm not sure I can find a nice Pythagorean triple that does that. Hmm. Now this 209 that we've got here, it's too big, but okay, let me bounce something off you for a moment. It's a squared minus b squared, and that turns out to just be way too huge. It's got to be a plus k here over 2b squared. Hmm. Well, can I... I'm trying to think of Pythagorean triples here that would help. And maybe all even ones. Like, I tried the 6, 8, 10 a little while ago. Now, what if I did something like 16, 30, and 32? Because that doubles the last one that we just had. But now I've got more options. So if I look at things that are multiples, I've got more options for what b can be. So I was forced to make b a, or b before, based on this 8 before. But now, if I let a be 16, b is 15, a is still bigger than b, but now they're really, really close. So this, I think, might have a slightly better chance of succeeding. All I needed to do was give myself more options. I was running out of primitive Pythagorean triples that I could work with. 20, 21, and 29 was sort of the last one that I can really think of off the top of my head without having to remember the formula for them. This is promising. So 225 minus... Oh, sorry, 256 minus 225. Times 16 plus 32 divided by 2 times 225. Okay, so that's 31 times 48 all over 250. Let's see, we can divide top and bottom by 2. And that's sadly about it, but this is definitely going to be greater than 1. So this would satisfy, A is going to be the biggest one, obviously. So this would satisfy A is less than B plus C. Because, I mean, just a cursory glance, the top is more than 600, so your C is at least 3, probably. Definitely at least 2. So that's true, but the problem is I don't get a nice integer for C. But this shouldn't be a problem. Because if I were to go ahead and multiply what do I want to do here? Because the original expression we started off with was a squared minus b squared minus b squared plus ac is b squared times c squared. And if I were to replace a with r times a, so if I were to scale it up with a similar triangle, and the reason I thought of this is because the only thing that really defines this relationship is the angles they give us at the start, so you can scale your triangle as much as you want. And the angles will stay the same, and so the relationship should stay the same. So we'll bring out a factor of r squared from this bit, and a factor of r squared comes out of this bit. So the specifics of the a, b, and c being integers is not that much of a pain because you can always just choose your scaling factor r to keep everyone, to make everyone an integer as long as they're rational. I wasn't too worried about that 2b squared there. So that's r to the 4, and then this part here becomes the b squared c squared, but then you can change that to rb squared rc squared. So I suppose if we can say if rational a, b, c satisfy the equation, so will RA, RB, RC, and we can choose R, so these are integers. So I've seen that A being 16, B being 15, and C being, what was it, 31. 31 times 24 over 225 works. So that's nice. So then let R be 225. And so what will you get? You'll get A is 16 times 225. So 360. B is 15 cubed, actually. So that'll be 337. And C will be 31 times 24, which is 744. These are integers. They satisfy the triangle inequality, so you can definitely make a triangle. Because the biggest one, A, is definitely less than 4,000, which is less than the sum of B and C, the two smaller ones. And I'm confident from my work before that they satisfy that quadratic in C, but we can double check that A squared minus B squared plus A squared minus B squared plus A times C is equal to, so 3600 squared minus 3375 squared. Big number, 1569375. 1569375 plus 3600 times 744. 2678400. So I'll add on the 1569375, multiply it by 1569375, which is something my calculator sadly will not display properly. But it should end in a couple of zeros here. No, it should end in 25, actually. But I'll just work it the other way. So then B times C was 3375 times 744. 271,100 squared which is, for some reason, a different number than what I've got here. Well, that's not good. I really hope it doesn't come back to this me screwing up this expression. Oof. I got my numbers right. Yeah, 3375, 744. So BC squared should end in a whole bunch of zeros here. We've got something that ends in fives and something that ends in fives here. That's not gonna play nice. So I've done something wrong. Where, I can't say. It's probably got to be I started off with the wrong expression. I'm certain that that's got to be it. So let's try and go for that quadratic again. Go right from the source. It is a squared minus b squared minus b squared plus ac equals b squared c squared. Okay, so I'm going to say b squared c squared, a squared minus b squared, a squared minus b squared plus ac. So that's a squared minus b squared squared plus a squared minus b squared c. And then we can say, well, that's b squared c squared minus a squared minus b squared c minus a squared minus b squared squared has got to be 0. So c has got to be negative b plus or minus, although I'm pretty sure it's just going to be a plus, square root of b squared minus, but we've got another minus, so it's plus 4a c all over 2a. Now, we already observed a has got to be bigger than b, so we're going to have an a squared minus a b squared here. I'm not going to do anything about that 2bc, or 2b squared there. Then we'll have a plus or minus the square root of a squared plus 4b squared. And this has got to be bigger than a, just on principle. So it's got to be a plus. So that looks exactly the same as what I just had a moment ago. So if I plug in C here, so if I take my 3600 and I square it, and I subtract my 3375 and square it, yeah, so what I'm trying to do, I'm trying to plug in the A and the B, because clearly they don't have the right relationship for the C here, which is a shame. Because everything should scale and still satisfy this expression. And yet it doesn't. Which is super annoying for me. Did I maybe calculate the C wrong in the first place? So what did we have? We had A is 16, B is 15. 256 minus 225 is 31. over 2b squared is not 250, it's 450. Times a plus the k, which in that case was 32. And that adds up to 48. (48) divided by 2 is 24. 450 divided by 2 is 225. There's no other factors I can get rid of. Oh, wait, no, I could get rid of... there's a factor of 3 on the top. So 48 divided by 6, I could have 31 times 8. And then 450 divided by 6, I can get 75. Now, if I made c equal to 31 times 8, b would have to be 75 times 15. A would have to be 75 times 16. So that'd be 248 for my c value. But does this a and this b, when plugged into the original expression, still equal what I want it to? And I don't think it does. So that'd be 1200 squared minus 120 or 1125 squared, all over 2 times 1125. In this case, the new k I get is 2550. So then we get 1200 times 2550. 1200 squared minus 1125 squared divided by 1125. I'll get 155 over 2 times 1125. 1200 plus 250, 2550 is 3750. Divide that by 1125, you get 3.3 repeating. Divide that by 2, multiply it by 155. Yeah, something's hinky, something's wrong. So the c value that I get doesn't scale the way it's supposed to. Because I didn't get 248 there. Just redoing my calculation here. Yeah, I'm off by just a little bit. I get 258.3 repeating, which is not what I want. I have just made a terrible mess of this question. So why isn't it working? I should be able to scale up. If I can get an A, B, and a C that satisfy... Although I never tested whether or not these really do satisfy the expression. So that could be a problem. I'm not quadratic formulaing properly. Hmm. Ugh. Fine with my answer, but I was fine with my expression for C here. That went quite well. And then that darn 2b squared at the bottom, I feel like that's the culprit. And here I wasn't very worried about that. Well, let's see if this b, and this a actually satisfy the expression. So that should be 31 times 31 plus 30. A is 16. And that should be b squared, 31 times 8 over 75 squared. Those parts will cancel out, and so it'll be 31 squared, 8 squared over 25. Got a 31 here, and then 16 times 8 times 31. I can definitely take out another factor of 31 here. And you get a 1 plus 128 over 75. So 31 squareds go away. And then 128 over 75 plus 1 multiplied by 25 is not 64. Not 64, so So my answers here don't seem to satisfy what we're looking at. So is this expression not correct for C? But it looks like I did the quadratic formula right. There it is. It's not a 32, it's a 34. There it is, ladies and gentlemen. That's the thing I've been stuck on for the last 30 minutes. It's a 34, not a 32. Did I at least have a 30? No, I've had it the whole way through. That's... There it is. Okay. So, let's try this again with 34. So we should get 31, 16 plus 34, all over 450. That should be my C value. And then, so that's 50. So we'll get 31 over 9. Scale everything by 9. So make C 31, make A 144, make B 135. Is that going to work? Let's see. Okay, so hopefully for the last time, 144 squared minus 135 squared, 2511, 2511, plus 144 times 31. 4464. And then 135 times 31 is 4185 squared. All right, so 4185 squared divided by 2511 is 6975. Subtract 2511. And wouldn't you know it, there it is. Well, I feel awful and embarrassed. There's a solution. So, turns out I had this. I had this a long time ago. I had this right from where I had my little freak out here. I had it, I had the wrong K value. K should be 34. Didn't double 17 properly. I know one mathematician who's going to be quite angry with me. I don't seem to know my 17 times tables. But the work here with scaling was good. And it just took forever to find my error. And even the original, I had to plug in my little values of C to see if the scaling was screwing up, and I had the wrong Pythagorean triple, so I'm sorry I wasted everyone's time. But there we go. It wasn't that bad of a question I didn't find. I thought the geometry parts in A and B were quite nice. And C wasn't too bad, I guess. I mean, I really wish I'd caught that 34 earlier, but oh well. But there we go. 2011 is done. If you're looking for more Euclids, feel free to browse around the channel. The 2012 Euclid, of course, is on its way, and 2010 has been done. So feel free to poke around, and if you're looking for other written contests, the Fermat, Galois, and Hypatia are also great things to look at. But that's it for me. I'm going to go rest my voice because it's been, probably more than an hour, I'm sure. But take care and have a wonderful day.